Up to this point, you have been exploring how computers learn with machine learning through fitting internal parameters of a function or a neuron to match X and Y values together when there was a linear relationship between them. This is often called regression, where you are using a neural network to predict a single value from one or more inputs. Another common use of neural networks is classification, where the network can tell you something about the data. For example, if there's an image, it can tell you the contents of that image. Or if it's a set of values describing an object, then it can tell you what that object is. We'll now look at how we can move from our single neural example to multi-neuron, multi-layer networks, and how to classify content. To this point, we have been looking at a single neuron and using it to get the Y value for an X when there's a linear relationship between Y and X. But neural networks can be more sophisticated than this. So for example, we have a neural network with two layers, the first with two neurons and the second with one. The neurons in the first layer each have an internal W and B that they can learn, and they will then output to the second layer, which will calculate based on its inputs and not the X's directly. So a single output layer like this, we can do a regression when we calculate a value like we've been using all along. We can also have multiple neurons in the output layer instead. This methodology is often called classification. So if we want to design a neural network that can tell the difference between a cat and a dog, we could have one output neuron for the cat and the other for a dog. So that if the image of a cat gets fed into the network, the neuron representing the cat will have a high probability value, and the one representing the dog will have a low probability. And similarly, if we feed an image of a dog, the neuron representing the dog will have a high probability, and the cat will have a low probability. This gives us a way of labeling cats and dogs by having our label contain the desired output of a set of output neurons. So if our first neuron represents a cat and our second represents a dog, then we can say our label for cat images is 1, 0, and our label for dog images is 0, 1. Or if you want to create a network that recognizes handwriting digits 0 to 9 with an output neuron representing each, we can use labels like this, where every output neuron is 0 except the one representing the digit. So let's look at some code that will use a neural network to recognize the digits 0 through 9. We'll need data, images that are labeled to train with, and fortunately, there's a data set called MNIST that's already built into TensorFlow. With these two lines of code, we can load the data. The data set is split into training images and labels, as well as validation images and labels. The data set looks like this. There are 60,000 label images and you can use for training, and 10,000 that you can use for testing or validation to evaluate how good your training is. And we'll get all of this by simply asking TensorFlow for the MNIST training and validation sets. The handwriting digits are 28 by 28 monochrome. That means each pixel value is from 0 to 255. We want to normalize these to use them in a neural network, which behaves much better if the values are between 0 and 1. So we can divide the image values by 255. So next, we define our neural network. Earlier, you learned about sequential and how sequential can be used to define a neural network by listing the functions of the neural network. And that's what you're seeing over here. It's a little more complex than the single neuron that you previously saw. Our images are 28 by 28 in dimension. So the first thing we can do in our sequential is define an operation to flatten these out so we can feed them into the neural network. The next layer is 20 neurons. So we need our images to be the same dimension as the layer considered to be 20 by 1. So our images will need to be something by 1 in order to fit. The easiest way to do this is to flatten the 28 by 28, which is 784 pixels, into a 784 by 1. And that's what flatten does. Well, we'll tell it to expect the input shape to be 28 by 28. And if it gets anything else, it'll throw an error. Next, we'll define a layer of neurons. We'll have 20 neurons in this layer. This number is purely arbitrary for now, and later you can explore methodologies to pick the optimum number. Too few, and you may not have enough to learn the contents of the image. Too many, and you can over-specialize, or your network can be slow to learn. The activation function is a new concept, and we'll explore shortly. The final layer will have 10 neurons in it because we have 10 classes, the digits 0 through 9. It also has an activation function that we can explore shortly. So our network with 20 neurons in one layer and 10 neurons in the other will look like this, where we have each neuron connected to every other neuron in the layer, in the other layer. All of these connections inspire the word dense for this layer type. We will want to feed the pixels of an image into this neural network. So for example, these pixels are one of the training images. It's the number 7. We would like that the neuron representing the number 7 is the one that would light up. And we'll train it with this set of zeros and ones as the labels representing 7. So remember that our image is 28 by 28. So instead of a square image like this being fed in, it'll be flattened into a 784 by 1 that is fed into the neural network instead. So if we return now to our neural network architecture, we can see this definition: the flattened layer to flatten the images, the dense layer of 20 neurons, and the output dense layer of 10 neurons in our 10 classes. Our layer of 20 neurons has something called an activation function on it. It's called ReLU, which stands for rectified linear unit. The important thing to know is this, that every neuron will call this activation function. The ReLU activation function changes any output that is less than 0 to 0. So when we evaluate y equals mx plus b for any of these neurons, we will throw away any values less than 0. This is commonly used in dense layers so that the neurons don't cancel each other out. Imagine if one of these neurons returned a value of 10 and the other returned -10. Without ReLU, we'd get a net of 0 from that pair of neurons. And in general, we don't want this. For the math inclined, you might also notice that this can introduce a nonlinear relationship between the layers, which helps you to capture complex relationships beyond just what the neuron alone can do. Our output layer has another activation function, this time called softmax. What this will help do is help us find the neuron from amongst the 10 that has the highest value. It saves us writing code to loop through the outputs and pick the biggest one. Our process of compiling and training is pretty much the same as we had for our single neuron example, with the key difference being the functions we use for optimization and loss. In this case, we'll use an optimizer called Adam. TensorFlow has many built-in optimizers, so instead of worrying about the math for optimization, all the gradient calculation and descent stuff we saw earlier, we can just pick a function and use it, making it easy for us to experiment. Adam is particularly useful because if you recall when we spoke about gradient descent and the jump size from the learning rate, well, Adam can vary its learning rate, helping us converge more quickly. And we can say the same for loss functions. There's a menu that we can choose from, and often our loss function has to map closely to our scenario. For example, when we were doing regression, mean squared error made sense, but it doesn't for classification where we have a number of categories instead of a single value. and we need the loss across the categories. This means that you'll need a categorical loss function like I'm using over here. Model fit.fit runs the training loop. In this case, we can train for 20 epochs. And we can test how well our network did by calling model.predict on one or more images. Here it's running it for the entire validation set of 10,000, but I'm just printing out the classification it gave me for the first one and comparing it against the actual label. This set of 10 numbers is the set of 10 probabilities for each of the 10 values as output by the 10 neurons. And the 7 is the label of the first image, so we know it's a 7. If we inspect closely, we can see that the neuron representing 7 has by far the highest value. It's telling us that we have a 99.89% chance we're looking at a 7. If you look closely, it's the 8th neuron because we started counting at 0. That is, the first neuron is the probability we are looking at a 0. The second neuron, the probability that we are looking at a 1, and so on. Next, you'll try this out for yourself, and you can inspect the neurons in each of the layers to see what they have learned and how this maps to classifying an image.